two main things. First, we'll look at a relatively thick wall where we use the K concept that we talked about. And then I mentioned to you R curves when we were talking about whether the plastic zone is small enough to do the analysis. So we'll do a case that's actually probably the most common with pressure vessels, where you have a thin wall, and when you start a crack, you really tear it, as opposed to popping the whole fracture. So it will propagate as a crack, but it's not going to be a rapid propagation. It will just be based on displacement. As you open it, it's going to break more, essentially. Whereas the other test that has this pre-crack in the sample, a lot of times when you reach the critical load and it starts to propagate, it will pop. And that's why it's a little easier to get our fracture toughness from those curves, because there's a fixed point where now the sample doesn't sustain the load. And when you're tearing, you need a criteria for how much tearing is okay, as opposed to, oh well, keep tearing it and it's gonna, you need a criteria to say it's enough, essentially, when you're tearing, and that's not something you need when you're dealing with a thick wall. As far as schedule, next week, so we don't have a lecture tomorrow. There's going to be a video, I believe. There's a video tomorrow, and then Monday, Professor Eager is going to be teaching. Tuesday, Wednesday are going to be videos. Thursday, I'll essentially be wrapping up everything we talked about over 12 hours we spent together. So that's going to be the end of it as far as my part on use of materials. And Friday, Professor Eager is going to be teaching. So that's the schedule for next week. So pressure vessels. There's a code by ASME, American Society for Mechanical Engineers, called the Boiler and Pressure Vessel Code. It's used a lot. There are different divisions, which means that there's one division that will give you a very prescriptive approach to design. They'll tell you what to do. The other one will tell you how to do the analysis. And then it's a little bit more appropriate if you're doing a new type of design that doesn't have a standard geometry, for example. So it covers both. But I did want to point out that it's essentially looking at everything. It's looking at the material, how to analyze the loads, and it's looking a little bit into fabrication. If we're looking here, there's section 9 on welding and brazing qualifications, for example. So it will tell you what kind of procedure you need to do almost each new project or each new geometry to determine if such welder and such procedure can be used for your design. So it's relatively prescriptive. One of the reasons is, to some extent, that pressure vessels there's a safety risk associated with a failure, and I think that's a little bit why it's regulated in such a way. They have additions to it, so it says pressure vessels, but people will still use sometime the same code for designing other things that are not going to be pressurized. It becomes up to the designer. We talked about AWS last time as a way to say, oh, make my welds this way. So this is another one. And if you're making a special structure, you have the option, essentially, of going with ASME or AWS, American Welding Society. These pressure vessel that we talked about, that was probably 2 lectures ago. We did talk about not having square ends, because when you're loading it, you will open the corners. So what we have here is an intermediate geometry that has a corner, but it's not at 90 degrees. It has some angle to it. And just to recap on this one, because it's something very important. The way you would want to build it is, say you have your flat sheet for the central portion, and typically it's going to have a seam weld going all around it. And then you manufacture ends that will look like this. Could be just stamping, not necessarily deep drawing. It's not that hard to form that little flange. But the idea here is you put your weld at this location, so I'll put it as good and here as not good. Because when you apply the pressure, over here there's no bending moment in the wall, whereas at the corner here you'll have a bending moment. This whole surface will try to expand. It's a mistake that's done a lot, and I think it's important to keep in mind again that you could go and say, oh, I'm going to use very high strength steel, a 200 or 300 KSI strength steel to make a pressure vessel like this. But then you have to think about how you're going to put it together, and that's what we talked about last time with all the welds and issues with welds, because on a pressure vessel it's very rare that the pressure is going to be absolutely constant. So it will go up and down. Depending on the environment, you may be at risk for stress cracking as well. And stress cracking of welds is a problem because you have all these residual stresses. So if you take a plain piece of a stainless steel, for example, 316 stainless steel, and you put it in an environment that could generate stress cracking, it may do fine because it doesn't have high residual stresses. But if there's a weld on it, just in the heat affected zone and in that area, there's so much residual stresses that's the equivalent of almost loading a full sample close to the yield strength. And that's where the cracks will start with respect to the environment. So it does bring the idea of joining being, we listed about 9 sections of that code, and welding is one of them. So it does come into play when you build structures. The hoop stress is about twice as high, so that tells us from the geometry that I've put on the board that we'll be more worried about that seam weld that I've put on. So if it's a thick piece of steel, we'd be looking at making a high quality groove weld that we talked about. If the vessel is big enough, we'll try to weld from both sides to avoid having a root that has defects in it, or imperfections anyway. So it's kind of the approach to think about when you really go out and say, oh, I'm going to build this. Now, a lot of things end up breaking. Sometimes it's an overload. So on a pressure vessel, if somehow you go above the boiling point and you have a little hole and it's over pressure, it will burst eventually. And the question becomes, is it going to be a catastrophic failure or just a leak? And I thought I'll bring that topic to you as something to think about. In the context of pressure vessels, what it means is it okay to have a crack that will go all the way through the thickness of the wall without fracturing the whole tank? And if that's the case, then you depressurize at that point. So there's nothing that blows up, as opposed to having a crack unzipping all around the tank. And both happen. I didn't scan it, but there are plenty of examples of tanks that were nice cylinder and they spread apart because at some point the crack became unstable. You reached the fracture toughness before you started leaking and lose pressure. So if we are to design a tank, that's an example I came up with. Say it's a 1 inch thick And we wanted to decide what kind of material we can use if it needs to leak before it breaks. So we want to avoid a catastrophic burst of the whole tank. So we have these equations for a semi-elliptical crack. The one I picked, so this is, we're looking from the top now of this. We're looking at the wall. We're forgetting about the well right now. Oh, it should be a hoop crack. So let's do it the other way. So it's just flat. So that's 1 inch thick. And say that's the outside and the inside. Our objective is to grow a crack, say like this, so an aspect ratio of 2. From here, going towards the inside, so our A here is 1 inch. And if you're looking at the schematic for the semi-elliptical crack, we'll put this as 2 inches. The solution will vary a little bit depending on how you estimate the crack geometry, but not a whole lot. So I'm using this as an example, but it essentially means I'll have 4 inches of visible crack on the outside before I start seeing the crack on the inside. It's not unreasonable. Now, just from this information here with A and C, when I calculated, I got this factor of 1.28 that I plugged into the Q. To evaluate Q, you have to decide a stress level. So I put 80% of yield, thinking that I'm not going to grow the whole tank yet. So I'm below the yield strength for the pressure vessel. If you have catastrophic conditions, sometimes the ratio could be 1. You could be at yield. But it's in that range of number. And again, it will vary some, but we're just doing this here to get an idea. So I get a Q of 1.5, and that was for stress level. That's actually running in this direction here. So we have sigma over sigma y of 0.8. That's what we selected. So this becomes pretty straightforward. We have our then we have to decide a stress level. So if we're taking this as being mid-strength steel, so we could say our stress level is going to be around 50 KSI. It wouldn't be the allowable normally, at least not for mild steel, but say it's over pressurized by some amount. So we have 50 KSI. So now if I put all that information into my K1 that's on the board, when I did it, I got K1 80 KSI square root of inch. It's reasonable. I can do that. I can find good quality steel that will have a yield around 60 or 65 and a fracture toughness around 80. But it's not far from the limit. So that's what I picked the numbers to give you an idea that as you start, so if you have a 1/4 inch wall, you know it's easy to form a crack through the thickness before you break, so you don't have to worry about it. As you go up in thickness, there is that critical point where now you really have to worry about it. If you have a 6-inch thick vessel, most likely you'll have to inspect it for cracks on the outside, and they do that in power plants quite a bit. You look for cracks on the outside because you're not going to have a warning. It's not going to start leaking before it cracks open. So it's just part of your design. You would like to have the leak normally. I'm not saying all the time, but normally you like to have the leak before it breaks. But this is the kind of analysis you have to go through. So all we did really is we said, okay, this is my thickness, and then went through all the way to, well, this is the fracture toughness I need if I want to be able to grow the crack and not having it pop on me, dealing, to overload final fracture. You can do it the other way around. I decided, another case I did was a milder steel. If I have a milder steel, I got two effects. So I have this equation here of K is 1.12 sigma square root of Q, and then crack length here. If I go to mild steel, this number is going down and this number is going up. So I quickly get to a much greater thickness. And I got the order of 6 inches. And that was using pretty much the mildest steel I could find. They would have a fracture toughness around 200 KSI square root of inch and a much lower yield. So there's no way you'll reach higher value. So if you're thinking about, if what you're thinking about is safety, and weight, for example, is not so much of a concern, it's obviously going to cost you more to make it out of a mild steel, but if you can avoid a catastrophic failure in some situation, it's worthwhile, and that's why they do it. So you end up with probably twice as thick of a wall, but it's still going to leak before breaking, as opposed to leading to a catastrophic failure. So I'm mentioning this in context of tanks, but it's also applicable to pipelines. Although pipelines, if they are underground, if they burst, you don't want them to break, because a leak is not good by itself. So whether it's a burst or just a slow leak, sometimes it's not so much of a concern. And they will go and try to use 100 KSI steel for some application. Now, when they're doing it, they'll manufacture it so they don't have a seam weld, because that's twice as high of a stress. They're only going to have butt joints between sections. The only way to make it work. So if you go and try to repair it, chances are the crack is going to be in a direction that's very hard to repair. You have to stiffen it if you really want to extend the life. So it's not super complicated. When you hear leak before break, that's all there is to it. You have to, and we didn't talk about this, but this crack can come up just by stress cracking, which we mentioned. That would be just growing slowly under a steady load because of the environment. Or it could be this cyclic load because of pressure variations. It could start from an initial flaw. So maybe you had an imperfection here that created it in the first place. Maybe it starts from the toe of the well. That's actually likely. But at the end of the day, it's the same idea. When it's that big, when it's 4 inches across all the way through the thickness, you're starting to look at the bulk properties of that steel that you have to determine if this K value is reachable. So you can go all the way in. And one of the issue sometime is this will become a little ligament, and it will be in a plane stress condition, so it's not going to be as constrained, and it can pull and essentially prevent the leakage. So you do need some safety factor, if you will, in this whole analysis, because as you get close to the end of the thickness, the sample will be more free to stretch as opposed to cracking. So this is the thick wall case. Any questions on that? We could spend a whole class, but I figured in the interest of time we'll. Okay. So if you have a thinner wall, and you could do it with even cheese. If you take cheese and you start cracking the cheese, it doesn't pop on you. You need to keep pulling on it to break it. So that's what we're talking about here when we're talking about a thin plate. It doesn't matter how sharp the nuts you put in it. You can do a fatigue pre-crack in it. When you start loading it, it will tear on you, as opposed to really fracturing and making this popping noise. It's mostly an effect of being really in a plane stress condition. So the sheet can become thinner in the thickness direction, close to the crack where we have all those high stresses that we talked about. So when that happens, you get a lot of deformation. And deformation means it's not separating at the crack tip. It keeps blunt. It keeps blunting more and more as you go. So that's really what happens. This is just a schematic to show a lot of times the crack will start in a circumferential direction, even if it's at a well that's running around, like for our cap over there. Yeah, that's pretty much what it is here. But then it can decide to go the other direction if to follow the weld, if that's the region that's weakest. So whatever is the exact detail you have, eventually you end up with a crack of a certain length. And you want to find out if that crack is stable again. It's a leak before break situation that we're trying to check here. Or if it's not going to be. And the answer normally is it will. So this was maybe a 3-foot diameter tank, 2-3 foot diameter tank, and you were allowed to have a crack a foot long over a 1/4 inch thick before it starts to pop. Now you'll ask me, how did they get a foot long crack in there? The answer is they had a little membrane on the inside that was essentially sealing the crack, and therefore they did get an overload, a catastrophic failure. So the purpose here of running the calculation was to know how bad the situation was. And there had to be some rust and some indication on the outside of the tank when you get a foot-long crack. But the fact that they had this rubber membrane on the inside made a difference between completely releasing the pressure inside that tank or bursting. Now, I said that it's more tricky to deal with the material when it's ductile, when you have a lot of plasticity. I mentioned about it before, so now it's called the R-curve. It looks complex, but it's not. The solid line is the test result. So if you take a sample that's got initially a crack of length A0 and you load it, you can figure out your K value based on the crack length and the load you're applying. So that's the vertical axis we have here. Eventually, the crack's going to start to grow. So that's the curve here moving to the right. And eventually it stabilizes. So here, maybe we think of it as a sheet of paper. You started tearing it, and then it's so big of a crack that now it's the same load to keep going, essentially. Now it turns out it's hard to decide on a curve like this that's so smooth what to use as a material property for design analysis. If you were to pick this point here, when it starts to grow, I'll probably agree with you that you can do it, but it's very conservative. If you are in an application where deforming, stretching a little bit is not a big deal, then why not? Why not allow for it? So that's the idea behind that technique, to look beyond, if you will. This will be the equivalent of the yield point on a stress strain curve, but now we're talking about the tip of the crack. And if it's a mild steel, there's no way really for that steel to not yield and give that smooth curve. That's why the way to do it, the way to decide on a critical parameter for a fracture, is to draw these dotted lines. Now the dotted lines, they don't come from the lab test. They just come from the equation that we have on the board here for K is the load square root of crack length with some constants into it. So it's just a general equation, and they drew 3 curves, but you can draw 100 if you want. These are not actual tests. There's no cost associated with doing this. But the idea is you find whichever curve, and you see it's got this nice curvature, and that's because the square root of A that comes into play here. So you have this nice curvature, and what you're looking for is where the 2 curves become tangent. And that gives you, they call it the KC, but it's probably better to call it the KR, because it does refer to the way by which you evaluated it. I didn't show you those curves, because you could draw this curve for a material of greater thickness, but it will just show a straight line, and then eventually it pops. So there's no point to it. The reason we're talking about it here is we have so much blunting that we need a criteria to decide when it's enough, when it's our limit of what we consider acceptable load level or solicitation, the K value. So it's essentially using fracture mechanics, but now we know that we have a lot of plasticity. We are in plane stress condition, and we're just using the fracture mechanics to look at the load applied. And when it comes to the material capacity, we do this approximation using the tangent approach to determine what we call the critical K. And it's the same approach as we talked before for K1C. So when we have K1C, we normally mean plane strain, so great thicknesses, if inches sometime, depending on which material you're talking about. Here we're talking of the order of a 1/4 inch thick, maybe 1/8 of an inch, depending on the material, or less. And you have to run the test for each thicknesses, because you don't know where the results are going to be. It will vary quite a bit, actually, from one thickness to the other. But you don't have to do all the different crack lengths. So it's still, it's not super intense of a testing program. If you have a specific application for a tank of a given thickness, you can go and look at a few materials and determine how much they can take in terms of K value, even if they are into this tearing and, I'll call it extensive deformation mode, as opposed to a more macroscopically brittle behavior. When we're talking about a thick piece of steel, you don't see the opening in the crack. Okay, it's cracking, but it's not yielding all around. In this case here, you can see through. So you have this gross yielding and opening of of the crack. That's the difference. I think, I think I have the standard here. We're not going to go through the details, but I did want to bring it up here because that's an ASTM. I don't know how many of you have used or seen those. It will tell you everything. It will tell you what size of samples to use, how to run the test, and how to do the analysis. So I picked the curve here. Obviously, it's always nice when you have an idea of what you talk about. So you have options for the type of samples to use. So these are plates with a bunch of holding point. You have some wedge sample. This is actually pretty easy to do. The idea is to do it in a way that people can use your data. If you go to the lab and crack a sample without keeping track of how big the crack is as opposed to the width of the sample and all that information, it may be okay if you're doing it same geometry, same loading as you have for your project or your service condition. When it comes to making a more generalized analysis that you can use for different locations, let's say you're going to run FEA or do something like that, a lot of times you end up having to run a standard test. Now, it doesn't mean, if it's your design, it doesn't mean you have to meet all the requirements, but I'm pointing it out because a lot of times you get some good ideas. If you read the standard, you realize, oh yeah, maybe I should do this. Well, this whole section, I don't mind about it. So it's a great tool, regardless or not somebody requires you to do it, or code or something. This is the compact sample that I drew a couple times. So with this one, if it's thick enough, that's what I said. It's nothing's going to happen, and it will snap essentially. But when we reduce the thickness, that's when we talked about it, and then we have that smooth curve. That's the equivalent of a stress strain curve. It's not a big deal. I mean, you can deal with it, but I'll tell you, it's harder to get R curve data than get K data because it's varying on thickness. So it does involve more testing, and the likelihood you find exactly the thickness you're looking for is not necessarily obvious. The good news is when you're dealing with something thin, you don't have to worry as much about the leak before break type situation. So you can use relatively high strength material, and it will go through the thickness, which just leaking doesn't mean it's good. All right, so it's still a problem, but at least you don't have this catastrophic failure. So that's a. I would say it's a typical standard. You have similar ones for doing a K1C test and a bunch of different tests. So it's useful to be aware of. I think you have access through the library to those. So if you really want to say, oh, you're talking about this test here and for this material that they ran, so you can actually find out what the test requirements are. Sometimes it's not applicable. Sometimes it doesn't matter to your design. Sometimes it may matter. Cup cone fracture, they're still here. So you guys looked at those a number of times. I'm not going to pass them around, but I want to go back because I think now a couple of things is I think you understand that if you load and you have that pressure in all these different directions, you're more likely to snap and start a crack than on the surface where it's free to move in the thickness direction. There's no restraint. That's why we have a neck, right? The neck is these surfaces start getting closer together locally because there's nothing holding them straight. And well, in the center, you form this funnel shape of stress lines that will increase your stress level, and that's why I superimposed it here. So you have the cup cone fracture on top, and somebody did this nice job of stopping the test before it completely popped. So at the bottom, you see the crack that's starting, and you see essentially the region that is playing stress on each side. And that's going to form the cup shape, these shear lips, because it's not as restrained. You're starting to have, again, these straight lines of stress going through the sample after you release the center. Now, you can have a situation, which is the right-hand side, where it's not quite as ductile. I mean, I don't see a neck there. Well, it's not that great of a... So we have a big neck on image B, but when we go to image D, it's almost a straight cylinder that fractured. And that's the condition that I want to introduce to you, because it happens. But before we get there, we'll go back to these crack propagation lines. For this type of sample, we're looking at a crack that starts in the middle because we have triaxiality, we have triaxial stresses. And typically the crack's going to grow fast, so it will be multiple cracks that go in different directions. And between them, we have that step that we talked about. And that's why after the fact, we can say, oh, this is where two cracks were meeting. And we call those the crack propagation lines. So we'll do it one more time. And it's good because we'll talk about, there are really just two types of lines. Well, there are some more, but two main types of lines to worry about when you're analyzing a fracture surface. So we have this situation here that it starts in the middle. And then when we see those lines going this way, this is what I'm referring as crack propagation lines.
How are you loading it?
It's loaded in this direction. So it tells me that here the crack was going this way, here the crack was going this way, approximately. Because I essentially had two cracks that were growing, and that's where they met as they were coming together towards the outside of the sample. And you have the same idea if we're at the corner. If we're at the corner and we see those lines going this way, we know it started here and it went all the way across. So on a lot of fractures, people will talk about these lines. So say now we start here on the surface, and for some reason here it's not really clear what's going on, but then you start seeing these lines going like this. That tells us that a crack was primarily coming through the center and then going up and down all the way to the end. So we would call those chevron lines, but they're essentially crack propagation lines. It's the same idea. So they move away from each other in general. So we'll talk about the other lines a little bit later. Right there. So now we still have lines that move away from each other, and I'll use my pointer here. So if I'm looking here, it goes this way, and it goes this way. So I know that this is towards the origin. The lower direction is towards the origin for that area. But the main difference on this fracture surface is it stops. Right here it stops. And then I start getting lines again. So that tells me sometime it is part of the same loading. It's just the crack will go faster and reduces the load, and therefore it stops. So it's kind of an acceleration, deceleration. Oh, I'm going too fast now. The K value is going down, so a stop. And then when I keep pulling on it, if it's a displacement condition, then it goes up again and starts. So that happens a lot with plastics, actually. This case, they say it was a two-step hammering process from a notch that was at the bottom. So it means that the load completely went out, and when they reloaded it, they started forming new cracks again. That's why the most straightforward line, I think, is on the top right, the line B, that tells us really, oh, this is where the crack was at some point in time. So it's a cracked arrest line. And it will run approximately perpendicular to the direction the crack was going. So it's another tool to determine the origin or the direction of the origin. In this case, we have one that's inclined with positive slope on the left-hand side and then negative slope on the right-hand side. So it does point to the bottom as being the fracture origin. It's not the most complicated one, but actually, I've done projects where we had like big clamps and end caps or anything, and you start looking at it. You don't need a microscope because it's super big, and you just sometimes get one of the information because it's dirty or something. So I remember once getting just a crack arrest line at one location, and then on the other side maybe 40 inches away. So I knew at some point the crack was from there to here. So it was not too hard to eyeball kind of in the middle of it where it started. So over maybe 20 feet of circumference, I was within a couple inch of the fracture origin. So we just picked a sample there to find out that there was something going on. But it's essentially it's practical, but I think now you really understand what's happening at a crack tip. It deforms. If you stop deforming, release the load, you're actually going to go to a compression cycle at the crack tip. You'll blunt the crack in the other direction. So when you load it again, it's going to be new initiation sites. It's just the way it is. And that's the case for plastics. That's the case for metals. It's not just stopping. It's releasing the load, and that's why when you reload it, you're not in the same condition. Same when we talked about fatigue, and that the fact you keep blunting and unblunting your tip. It's kind of going through a one cycle of fatigue here. All right, last concept that I want to introduce is the difference between brittle and ductile. When you're ductile, you'll form holes in the material before you separate the surfaces on an overload case. In fatigue, it's different, but on an overload case, so you have the particle that's location here on the chart, you're starting to debond. So this is just an impurity, essentially. In piece of steel, aluminum, anything. And it will stretch and eventually break. Now, what you see at the end are kind of bubble shapes on the fracture surface. So what you have on the right-hand side is a fracture surface that shows you rings, if you will, the white rings. The white on that image, because that's an electron microscope image, means it's very tilted. It's a ligament essentially that's stretching out. The ligaments give more response because of the high slope on this type of imaging. So it tells you that you form these dimples, we call ductile dimples for a ductile fracture. And embrittlement means, I'm sorry, here I should lower this. Maybe not. The other case, essentially you see grains. You have sharp edges, so it cracked through either between the grains or through the grains, but essentially with less ductility. And you can have secondary cracks. So if you're looking at the lower right image, you don't have only one crack, you have multiple cracks. So those are situations normally we try to avoid. Sometimes it's because of the processing. If in processing you introduce hydrogen of some form through the heat treatment, you're in a temperature range where you form hydrogen in the steel, and you keep it when you're cooling down. So you say you're cooling down not fast enough or not slow enough. These are situations you can run into. So there is, tuning, especially for steels, in terms of avoiding those situations. And the higher the strength of the steel normally, the more it becomes susceptible to these embrittlement processes. The lower the temperature is, also the more at risk for embrittlement you have. So we can get that information from the fracture surfaces. If you run a test, say, oh, this doesn't seem right, then you find out if you have a hydrogen problem or other types of problem with your material. That's what I had for today. Thank you for your attention.